Okay, today we want to start talking about generalized viscoelastic models, which are significantly more complex than kind of the simple models that we've already talked about. Let me just begin by reminding you of what we showed already with a Maxwell model. So we showed that for a Maxwell model, okay, and let's see if you can remember what that looks like. It's a spring and dashpot in series. So there's our dashpot, and there's our spring. We called this eta, characterizing the dashpot, and E, modulus, characterizing the spring. We also said previously that the quantity eta over E, okay, the quantity eta over E was going to be equal to tau, which we termed some sort of a characteristic time. Okay? Now, in real materials, a single characteristic time is often not accurate enough. So, in real materials, okay, a single characteristic time, so our single tau, is often not accurate enough. Okay? So what do we need to do? So we need some sort of a model that allows for multiple relaxation times. So we need a model that allows for multiple tau. Okay? And then sort of each one to have an effect. Okay? Multiple is the idea here. So to do this, we introduce what's called the Generalized Maxwell model. Okay? So we introduce the Generalized Maxwell model. And all the Generalized Maxwell model is Maxwell elements in series. Okay? That's Maxwell elements, or Maxwell models, simple Maxwell models not in series, in parallel. Okay? So what does that look like? Let's say this is the top of such a model, and we'll end up with having some spring and a dashpot there. And let's just call this now E1 for the first element and eta 1 for the first element. Let's do this, kind of go over here. And we could envision coming off and now adding another in parallel with that, where we would characterize that as E2 and maybe eta 2. And I'm going to just put a dot, 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 and we could go further and characterize now another one that's, let's say, E to the n minus 1 and eta to the n minus 1, not E to them, but just identifying the element they belong to. And then finally, we could have E sub n and eta sub n. Okay, so this would be a generalized n element Maxwell model. Okay, and of course we're going to pull on it just like this, just like we have in our previous when we talked about just the simple Maxwell model. And here I want to note, remember we had talked previously about the standard linear solid for the Maxwell model, which was a spring that was in parallel with the Maxwell element. This is actually can be represented with the generalized Maxwell model as well. So just say the standard linear solid, the SLS, Maxwell representation. Okay, the SLS Maxwell representation can be obtained here with a two-element generalized model, right? Obtained from a two-element Maxwell model. How about generalized Maxwell model? And let me show you how we do that. We basically we're going to set this eta 1 term to infinity, and when we do that, we have we basically negate the dashpot and we just have the spring that we'll call E1. And then we'll have a second spring in parallel with a dashpot there in series. That'll be eta 2. Okay, and that's our standard linear solid for a Maxwell model. Okay, so I'm just showing you that something we've already mentioned and talked about is a subset of what we're trying to now generalize. So let me make a couple observations to set up the equations. So and these are observations now of the generalized Maxwell model. Number one, first observation is that the strain in each element, element 1, 2, up to n, right? The strain in each element is the same. Okay? So the strain in each element is the same. Okay? So what that means is that we can write that epsilon, which is the strain in the entire generalized model, is the same as the strain in the first element, which is equal to the strain in the second element, which is equal to the strain in the n-1 element and the strain in the nth element. Okay? Let's go ahead and call that equation 1. The second observation is about stress, that the stress in the element is in the generalized model is the sum of the stresses in each element. Okay? So the stress is going to be the sum of all element stresses, right? So for example, right, this first spring in dashpot grouping, it would be the first element, right? So we can write then that the stress is equal to the stress in element 1 plus the stress in element 2 plus up to the stress in n-1 plus the stress in element n. Let's call that equation 2. So next we want to recall the governing equation for a single element, which we've already talked about in our simple Maxwell models. So let's just say that recall the governing equation, right, of a single element, right, which we said was epsilon dot is equal to 1 over E times sigma dot plus 1 over eta times sigma. Okay, let's call that equation 3. Okay, well, we've talked now about Laplace-transform, so we actually want to go ahead and do that. So let's go ahead and take the Laplace-transform of equation 3. And remember, we're trying to develop a governing equation for this whole system. So what you can probably see that we're going to do is, and I'll just give you the sort of roadmap. We want to solve for the stress in each element and plug it into equation 2 somehow. Because it's going to be dependent on the strain. So then we'll have a relationship between stress in the element and strain in the total element. Okay? So to do that, let's go ahead and take the Laplace transform, we'll call that LT, of equation 3. Right? And we're going to say that we have to have some initial conditions. So we'll say that, okay, for the case where epsilon of 0 minus is going to be equal to 0, and we'll also say that the stress is going to be equal to 0. So basically, there's no stress or strain prior to whatever we're applying. Okay, so that's our subject condition. If we go ahead and take the Laplace transform, then there's the Laplace transform of epsilon dot. If you remember from our previous lectures, looks like s times epsilon bar, and then now we can take the Laplace transform of this term on the right hand side, and this looks like s over E times sigma bar, and then we have plus 1 over eta times sigma bar. We can go ahead now and solve for sigma bar from this equation and say that sigma bar is equal to s times epsilon bar divided by the quantity s over E plus 1 over eta. Let's go ahead and call that equation 4. Okay? Now let's do a simple one. Let's take the Laplace transform of equation 2. So take the Laplace transform of 2. Okay? In this case, it's just going to look like sigma bar is equal to sigma 1 bar plus sigma 2 bar plus dot 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 plus sigma n minus 1 bar plus sigma n bar. Okay, we'll call that equation 5. Okay, so as you're probably going to expect, we're going to substitute equation 4 into equation 5. Okay, so substitute 4 into 5. And here we're going to say taking each element stress sigma I bar, right? So in equation 4, we just did it for a single element, but so for each element, this equation 4 is just simply sigma I bar, okay? So what that ends up looking like is that I have sigma bar is going to be equal to, and each term is going to have an S times epsilon bar in it already, so I can pull that out front and say S times epsilon bar. Now times the quantity, 1 divided by S over sigma 1 bar is going to, we just need to subscript 1 on E, and the same thing with eta. So eta 1 plus 1 over S over E2 plus 1 over eta 2 plus plus 1 over S E n minus 1 plus 1 over eta n minus 1 plus 1 over S over E sub n plus 1 over eta sub n. Okay? So there we have it. Substituting equation 4 into equation 5, let's call this equation 6. Okay. Well, that looks horrible. What do we need to do? Let's not be intimidated by the algebraic messiness at this time. Let's just acknowledge if we're adding fractions, what are we looking for? We're looking for a common denominator. We don't know what these are, so we need to get that common denominator, and we can't really assume anything about how one will be factored into the other, so we just have to multiply them all together. Okay, so let's get the common denominator. So to get a common denominator, I'll abbreviate that. You just take the product of the divisors. Okay. So take the product of the divisors in each term. Okay. So what does that look like? Well, that's if you're not familiar, we write a product similarly to how we write a sum. We use a capital Greek letter pi. So the product now from I equals 1 up to n. So this looks like the product of each of the denominator terms. So this is S over E sub I plus 1 over eta sub I. Okay, it's that product. And we're going to multiply equation 6 by this common denominator. Okay, so multiplying 6 by the common denominator, what do we end up with? Well, the left-hand side is easy. That just looks like, I'm going to try to pull this out so we can see where we're at. This is the product from I equals 1 to n of S over E sub I plus 1 over eta sub I. Okay, that's what we're multiplying it by, and then we just have this sigma bar. On the left-hand side, I'm going to pull out that S epsilon bar. So what we can write is that this is we have a sum up here, so we better have a sum down here. The sum, now this goes from I equals 1 to n. And what is it the sum of? Well, it's the sum of this product term from j now equals 1 to n of, let's see, of S over ej plus 1 over eta j, except one thing we need to be aware of here, and that is that this term looks the same as this, except it's been divided by whatever the denominator term was, so it's only the case for j not equal to I. Okay? Okay, let's call that equation 7. if you're just watching this and you haven't maybe gone through something like this before, you're just thinking this is awful. We're never going to get to a solution. So we need to actually ask, what does this give us? So what does this term look like? Well, really, this is s times some number plus some constant, right? So if I have the product from 1 to n of all these sort of constant times s plus a constant, that really is just a polynomial of order n. Well, we can easily write that. So this must be then the sum from I equals 0 to n of, let's call it p sub I times s to the I, where this is our polynomial coefficient, whatever that happens to be, okay? How about for this side? Well, this term, again, this is just the product term here. It almost looks like this side, except we are pulling out one factor. That's the factor that case that happens when I is equal to j. So this is one order of magnitude less. So it's a polynomial of order n minus 1. So we can write that as the sum. We'll call this now from j equals 1 to n of k sub j times s to the j minus 1. And I'm going to put another subscript on this I because because this is a single polynomial and it is a new polynomial for each value of I, okay? So we're actually summing a bunch of polynomials. So what we want to do now is simplify equation 7 to look like this. So let's just say simplifying equation 7, we end up with this left-hand side now looks like we're just going to replace this with this polynomial term, the sum from I equals 0 to n of p sub I s to the I times sigma bar is equal to, and on this side now we have s times epsilon bar, the sum from I equals 1 to n. And on this side now, we have the sum from j equals 1 to n of this term here, s j minus 1. Okay, so let's put it like this. We'll call that equation 8. Okay, we're just about to get to our final simplified solution. But I want to observe that what is the right-hand side? Well, it's really the summation of polynomials, right? This first term is a polynomial of order n minus 1, and we're just summing all those polynomials. So if you sum polynomials, you get another polynomial, and you don't change the order unless you're multiplying them. So really, this still gives us a polynomial of order n minus 1. So we can write this whole thing as, we'll call this now the sum from I equals 1 to n of, we'll call it now q sub I, and then we still have just this s, it's I minus 1. Okay, s to the I minus 1. Okay, and so what are we left with? So I can simplify now. So we can simplify now to get, and all I'm going to do is distribute this s term into this sum. So if I distribute that s term, I'm left with a left-hand side that looks just the same. It's the sum from I equals 0 to n of p sub I s to the I times sigma bar is going to be equal to this new quantity, which is just basically I'm going to take this s multiplied inside, distributing it into the sum. And so this now goes from s to the I minus 1 just to s to the I. And this now becomes the sum from I equals 1 to n of q sub I s to the I times epsilon bar. Okay, we'll call that equation 9. Okay, so I'm going to stop here in this part 1 lecture. We're going to talk about now how to go about getting it back to a form that we care about, but this is the development to get to a compact form in Laplace transform space for the generalized Maxwell model.